So the lead code problem we are going to solve now is called minimum cost to connect all points. This is a very popular question in my opinion. Why? Because we are going to be dealing with something very important that is called Prim's algorithm to solve this problem. And this Prim's algorithm actually has a lot of different practical applications that you can use it in all sorts of different questions and different techniques. So let's understand the problem statement. We are given an array points that represents an integer coordinates of few points on a 2D plane, which means x and y type of graph. And we are told that any particular point value is defined as xi and yi, so the coordinates of that location. Now we are told that the cost of connecting 2 points x and y is the Manhattan distance. So let's say that if you typically has like 3 values, and if you are trying to, let's say, connect any two like this one, in this case the cost of this one is going to be the Pythagoras if we try to choose the diagonal. But the thing is, Manhattan distance is that instead of picking out the value of the straight diagonal between these 2 points, you first go to a common point and then go to right. So in this case you are actually doing the delta of x and you are also doing the delta of y, so absolute values of x1 and x2 amongst these 2 points, and the sum of this is going to be the total distance you are going to cover. So this is called Manhattan distance, and this is what we are going to follow. So it's slightly better for us so that we don't have to spend so much time on calculating the Pythagoras or root values. Now we need to return the minimum cost to make all the points connected. Now let's try to understand this with an example. In this case, suppose these are the different points we are given. Now we need to make sure that number one, we connect all of these points in some fashion. And after connecting these points, we also need to make sure that the distance we are traveling by connecting them is the minimum distance we can. Now let's try to understand first of all that how does a Manhattan distance is going to work. So let's say you want to find out that what is going to be the distance between these 2 points, then logic is going to be quite straightforward. You are first going to do the difference between x pointers, so this y pointers, and you are going to add it to the difference between x pointer. So in this case the distance between these two nodes is going to be 4. Though it's not a diagonal, I'm just writing it diagonally so it becomes easier for us to understand. Now the thing is, the solution of this problem is something where we will have to deal with minimum spanning tree. Now minimum spanning tree is a very important concept in the graph theory, where you are given bunch of different points on any particular plane and you are trying to connect all of these points in some fashion such that there are no cycles being formed, and you are trying to span the tree in like only the places where it is absolutely needed, nothing more than that. But the question is, the first thing that should come to your mind is that, hey, in this case we are only given points, we are not given the edges, which means these are simply just the nodes we are given. We know in order to solve any particular graph problem we need two items. We need a nodes, and we also need edges. But the thing is, good thing for us is we already know how to calculate edge between any 2 points. And the thing is, in this case there is possibility that from every single point you are able to connect to every other point in order to treat it like an edge. But the thing is, if I try to draw the whole solution by that matter, it's going to look very bad, because imagine how many number of different edges you can form amongst all of these points, and then it is only going to look so much more messy and complex if you have to understand all the different flows and data entries and data points and whatnot. So what we will try to do is we will understand that what is the most simplest logic we can use to solve this problem, and we will also understand that how we are going to be using the Prim's algorithm and the solution of basically Prim's algorithm plus the graph theory concept to solve this problem. So let's start working on the solution of the problem. I hope you must have understood that what the problem is asking us to solve. So now let's very quickly and very simply think one by one that what are all the different possibilities we have across all of these 5 different points. Well, number one possibility is that if we are at this point, we don't know that what are all the points that are currently present inside the remaining graph, which means we don't know that if we have to generate a minimum spanning tree that crosses or that goes through every single nodes that are currently present, which node should this node 0 be connected to? So we don't know this question, number one thing, that what is the minimum cost to reach to any particular point from this node 0. And remember, we need to make sure that we don't form any cycles, because we simply need to connect all the points. And if there are cycles, basically our cost of connecting all the points would increase. So the shortest way to connect all the points is through like some sort of a straight line or a tree kind of structure where there are no cycles. So now at this 0, the number one thing we will have to do, if we have to find the shortest distance or the closest point, we will first have to calculate every single distance we can from all the remaining points to this 0th node. And the distance between these points would be treated as the edges, because we are basically connecting two different points. And amongst those edges, we will have to find the edge with the smallest value. So these are actually weighted edges. And the other thing is, the connection in this case is going to be bidirectional. Why? Because whatever the distance from this 0 to this node is, same distance is going to be from this node to 0 as well. So we don't need to do any directed distance calculation in this matter. All we are concerned about is unidirectional transfer, and to understand that what is the minimum place to reach that place. Now comes another problem. Let's say that from the 0, it makes logical sense that this is going to be the smallest distance that we can calculate. And we also know that the distance amongst this one is going to be 2. So sorry, 2 plus 2. So total, let's say that this distance is 4, that we already know that this is going to be the smallest distance. But once again, when we come back to this place, now we still have 3 more nodes that we will have to iterate over. We are not going to iterate over node number 0. We are going to treat that this 0 has already been visited, but once again we will have to repeat the same operation. And from this position, we know that the shortest distance we should be able to find is going to be this value. So if we calculate this, I think this distance is going to be 3. Okay. And same way, from this 3, the shortest distance that we calculate for any particular node is going to be this one. And this distance is also going to be 4. But the thing is, now we still have one more node remaining, and we already found the results for these 4 different nodes. So question is, how do we know that which node is actually going to call to this particular node? So for that, we will actually have to find a way that while we are calculating the distance from 0th node to all the other nodes, and same way from this first node to all the other nodes, we will still have to keep track of all the nodes that are still remaining. Because the thing is, it could be possible that there are some nodes that are not down the path of the shortest nodes. But the thing is, we need to connect all the points, so we will still have to find a node that is still closest to this node, that it makes sense to make that connection. Now I know what I just said might sound confusing, but the thing is, try to understand this from an example point of view, that if you are if we only traversed, or if we only use the greedy approach where we are just iterating in the minimum fashion, then we are always going to be stuck with one node that is not following this beautiful path. And the thing is, if we try to find the path to that node, that remaining node from here, this might be much longer compared to this distance. So in order to do that, what logical solution I'm suggesting is that we first start at the 0th position. From the 0th position, we make the calculation that how much time it is going to take to travel to this first node, second node, third node, fourth node, all of these nodes. Same way, then we find that amongst these 4 nodes, which one has the smallest value to reach to there, so smallest edge, and we realize that the smallest edge is 1 in this case. Then from this 1, we know that we already calculated the distance for 0. 1 is a self node in its own, which means now from 1 we will have to keep track that how much time it takes to reach to node number 4, 2 and 3, and keep all of these results stored somewhere as well, and then try to pick the smallest value that we can. Once again, from the smallest value, repeat the same operation for the remaining elements. So even from this smallest value, we will calculate these 2 distances. Once again, pick the smallest one, and then from the smallest one, see that what is the remaining value. And for all the remaining values, so for this remaining node, see that currently we should have 3 results. One result is between node 1 and this one node number 4. Second result is node 2 and node number 4. And third result is node 3 and node number 4, and amongst these three, whichever is the smallest one, pick that one, and that would be our solution. So now let's just try to walk through the whole solution that we just talked about and see that what are all the different concepts we will have to use to complete the solution in a manner that we are proposing. Now, first of all, what we need to do is we will need to make sure that there are no cycles. In order to make sure that, we will have to keep track that all the nodes that we have currently visited. So we can use some data structure like a hash set or an array or a boolean array of size n to keep track of all the values that we have visited so far. So let's say we will use hash set for now for our understanding purposes, but at the same time we are also going to be using array during the implementation. Okay, so let's say that we currently have our hash set that we are going to be storing to make sure that there are no cycles. Next thing is we will have to make sure that for every single node we calculate the distance to all the remaining nodes, find their distance, and we need to sort those distances. So in order to do that, one of the beautiful data structure we have is actually a heap, and we can have a min heap where from every single node that we start iterating over, for all the remaining values we will try to calculate the distance and put them in the min heap, so that it would be stored in like from in a ascending order. So smallest value would be at the beginning that we should be able to find. And how we are going to be storing the value inside the heap would be in this fashion, where the first value is going to be the distance and second value would be the point. So we would say that in order to reach to that particular point, what is the smallest distance that we will have to cover? That's it. That's all we need, because we are only concerned about the cost to reach to that point. So now let's see that first node is 0. In order to reach to 0, and let's say that we decide to start from 0. It's not necessary that we have to start from 0, but let's say that we decide to start from 0. So in order to reach to 0, what is the minimum cost it takes? So minimum cost it takes is still going to be 0. So we are going to be adding the value 0, 0 over here. Next thing is from 0, now we have 4 different options to choose from, that in order to reach to all of these values. So first value is in order to reach to, let's say this one is node number 1, node number 2, node number 3, and node number 4. So in order to reach to node number 1, the smallest distance it's going to take is going to be value number 4, and we will mark it as by 4, 1. Same way, if we have to reach to this value number 3, let's say that the distance is going to be 5 plus 2, 7. So we can mark the values as 7 and 3. Same way, if we have to reach to this value number 2, then the distance is going to be 13. So we can mark 13 and 2. And next thing is same way, if we have to reach to value number 4, then the distance is going to be 7. So we can still mark 7 and 4. And notice that we are going to be sorting these values because this is a min heap, so it would automatically be sorted. So the value would be something like this one. So 7 and 4, and then I think it was 13 and 2. So these are the currently 4 values that, or 5 values where we have so far. We will pop, and now we have started our iteration. So we will pop the very first element, which means we pop this value 0, 0, and we know that the cost to reach to value number 0 is 0. So we will also need to have a variable to store all the cost. So let's say that we have a variable that where we are storing all the cost. In the cost, we first add 0 because that is the cost to reach to value number 0. Let's say we kick out value number 0. The thing is, because we already visited 0, we are also going to be marking 0 inside our hash set. So let's say that this is our hash set and we already visited node number 0. So from now on, any subsequent entries that come in with value number 0, we are simply going to ignore that because we have already visited that inside our hash set. Okay. And let's keep on doing the iteration. Now the next entry inside our heap is node number 1. From node number 1, it takes 4 cost to reach to node number 1. So let's mark the cost to 0 plus 4. We are also going to be marking that 1 has already been visited so far, and we have this channel being established. Okay. Now from once again, from 1 we will have to repeat the same operation, because remember, from every single node what we are trying to do is we are going out in the breadth first search manner, not depth first search manner. So we went to one of the neighbors of 4, and then we are going to be visiting one of the neighbors of 1. Same way we are going to be visiting one of the neighbors of 3, and same way we are going to be visiting one of the neighbors of 4. So this is a BFS traversal, not a DFS traversal. And now let's just mark 1, and okay. So now once again we are going to leave all we are going to be popping these two entries, but these three entries like 7 3, 7 4 and 13 2 is still going to be present inside our heap. Now from this one, we have once again three options. First option is this one, the cost of this is 9. Second option is this one, the cost of this one is 3. And the third option is from 1 to 4. So the cost is going to be 2 and 5, so 7. So once again, we are going to be having one entry, that is 3 and 3, which is in order to reach to node number 3, we are going to be using distance 3. Next entry is in order to reach to node number 4, the distance is going to be 7. So next entry would be 7 4. So we can also put one more entry over here, 7 4. Okay. And we are going to be having one more entry, that is 9 2. In order to reach to 2, the distance is going to be 9. So we will have one more entry, 9 2 over here. And then the 13 2 would be like succeeded to the back end. And this is going to be the current values inside our min heap. Now once again, we are going to be popping out the very first element, that is the smallest element, that is node number 3. And in order to reach to node number 3, we will have to add cost as plus 3. So we will mark plus 3 cost over here. We will mark 3 as being visited because we already visited this one, and we will get rid of this entry. So now you can see that now the moment, let's say that suppose I'm just giving you for an example, suppose we say that this is the next closest node and we will try to extract this one. The moment we see that in order to reach to node number 3, it takes 7 cost. The thing is, we already visited 3 inside because it's present inside the hash set, so we can simply ignore this case. And same way, we are going to be ignoring all the cases that are going to be different from the nodes that we have not visited so far. Same way, from 3 to 4, we have this type of distance, and that distance to 4 is going to be 4 once again. So we can mark 4 4 because that is the smallest entry. And from 3, we will have to calculate one more distance, that is 2 up to this 2, and that distance is going to be 10 2. So we can mark one entry over here, that is going to be 10 2. But so once again, we are going to be adding cost 4 because we visited node 4. It takes 4 unit of time to reach to node number 4, and we have visited all of these entries. Now the thing is, we visited all of these. Now from 4, we will once again calculate the distance to 2. So let's say that this distance is going to be 15. So 15 to 2. So currently these are all the entries we have inside our heap. And let's see that what we need to do. So we already visited 0 1 3 and 4. We haven't visited node number 2. So we start popping values out. So we first pop this value 7 4 because we have visited 4, so we can just ignore this one. Same way, we can just ignore the 7 4. And then we have this node 9 2. So we pop 9 2 out. 2 we haven't processed, so we are going to be marking the node 2 visited over here and add this cost 9 over here as well. And now you can see that the size of our hash set is exactly same as the size of all the number of points that we are given, which means we have visited all the nodes and we can stop our conclusion. So in order to do this one, the moment we the size of our hash set becomes the number of nodes present, we can stop our calculation, and whatever the cost we found so far, we can return that as the answer. So in this case, the answer is going to be 20. And this is the whole solution. So I hope it makes sense to you that how did we calculated this. We dealt with a lot of concepts that how not to detect cycles. Then we also make sure that we had a hash set to understand that what are the nodes visited so far. We had a heap to find the smallest entry from any particular point, and we were doing all of this while calculating the cost of the minimum spanning tree. So this is a beautiful solution. If we understand the time and space complexity, time complexity is going to be big O of, first of all, let's imagine we will have to do n square work for any single node. Why? Because at this position, we will have to calculate distance between all of these 4 points. Same way at this particular location, we will have to calculate the distance between all of these 4 points. So we will have to do big O of n square work to calculate all the distance. And then we will have to find the shortest distance, and shortest distance we are finding by using a heap. So it takes n log n time in order to find the solution from the heap. So overall, the time complexity is going to be big O of n square log n. If we see space complexity, because we are storing all the entries inside our heap, it is also going to be big O of n square. So overall, this is an expensive time and space complexity, but given the scope of problem, we cannot do anything better than this one. So now let's quickly see the coding solution. So the very first thing we are going to do is to define the total length of given all the points that we currently have. This we are going to be using to check against that whether we have collected all the points or not. Then we are going to be initializing our priority queue, and this is going to be our min heap. Then we are also initializing a new boolean array to store that all the values that we have currently visited so far. So we are marking it as in MST, whether it is present in the minimum spanning tree or not. Then we are defining a new class called point. So let's understand this one. So we have a new class called point, and it only contains two values. First one is a distance and second one is an index. And we can see that we are going to be using this instance of this class to store values inside our min heap, where we are storing that in order to reach to any particular index, what is the distance that it takes, and then heap would sort it out for us. And the very first element we are adding inside the heap is that we are adding the very first value, value located at index position number 0 inside the points, and we are saying that it takes 0 cost to reach to those points, and this is how our priority queue works. We are also having a variable to store the minimum cost that we have been able to find so far, and we have a value called points connected, so which we can use it to compare it against the total given length of points to define that whether we should complete our iteration or not. Then we are running our loop until our points connected reaches to the total number of n that is currently present. Then we are fetching the very first value that we currently have out of the priority queue. So we are doing a poll operation and then checking that whether this point that we found out, this current point, have we already visited that current point. So we can check that using the boolean array that we have created. Then we are checking that if we have not visited, then we are going to be marking it as visited, and we are also going to be updating the minimum cost to reach to all the nodes by the distance that it takes to reach to that particular node, and we are also updating the value of points connected so far. So now we already calculated and visited that particular point, but the thing is we will have to still calculate the distance to all the remaining points from that point. So we are going to be running another for loop that is going to span across every single n that is currently present. First we are checking that any particular index that we are checking, have we already visited or not. If we have already visited then we can ignore. If we have not visited, we will calculate the distance by using the math.absolute points, and then we will add a new entry inside our priority queue by adding that ith location and the distance to reach to that ith location, and it would sort it automatically. In the end, we simply need to return the min cost that has occurred so far to reach or connect all the points, and this is the whole solution. So let's try to run our code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs beautifully compared to a lot of other solutions. It's almost 80% faster in terms of time complexity, and also 80% faster in terms of space complexity. So which is pretty great. Once again, the solution is present inside our GitHub repository, so feel free to go ahead and check it out from there. Thank you.